In this video, I'm going to show you some more examples of solving non-homogeneous second-order differential equations with the method of undetermined coefficients. The first example is y double prime minus y prime minus 2y equals 6x minus 4 e to the x. If you remember, the general solution, if we suppose y is the general solution, is the sum of the complementary solution and the particular solution. The particular solution is part of the solution that is related to the right side of the equation. But the complementary solution is the solution that we can find with solving the homogeneous corresponding equation to this equation. Corresponding homogeneous differential equation to this equation is this equation, y double prime minus y prime minus 2y equals 0. Always by setting the other side of the equation equal to 0, as we did here, we can get to a homogeneous differential equation. And by solving this equation, we can find the complementary solution. For solving the homogeneous equation, first we write the characteristic equation, r squared minus r minus 2 equals 0. For solving this quadratic equation, we can use the quadratic formula, or you can factor it like this, r minus 2 times r plus 1 equals 0. From this equation, r equals 2. If we set this equals 0, r is 2. And from setting this equals 0, r is negative 1. Because here we have two real distinct roots, the complementary solution is c sub 1 e to the 2x plus c sub 2 e to the negative x. If you want to learn more about finding the solution of a homogeneous equation like this, you can watch my video about homogeneous second order and higher order differential equations. So this is the complementary solution. Now we want to find the particular solution, the solution that relates to this. Because in this video we want to use the method of undetermined coefficients, first we have to write this general form of the solution. Note that here in the right side of the equation we have 6x minus 4, which is a polynomial of degree 1. Because of the degree x is here is 1, so this is a polynomial of degree 1, which is multiplied by an exponential function here. For writing the particular solution, for a moment, suppose we don't have e to the x here. So forget this e to the x and just focus on this. Because this is a polynomial of degree 1, we can guess that the particular solution, the y that satisfies this equation, must be, of course, a polynomial of what degree? Of course, degree 1. Because this polynomial is degree 1, we guess that the function, the y function that satisfies this equation, the second derivative of that function minus derivative of that function minus 2 times that function, it should be equal to this expression. Because here we have a polynomial of degree 1, it makes sense to suppose a polynomial of degree 1 is the particular solution. Note that if here we had a polynomial of degree 2, then we can guess that the particular solution should be something like this, a quadratic equation. And if it is degree 3, we can continue and write the particular solution like this. But here we have only a simple polynomial of degree 1. So we guess that this should be the particular solution. But don't forget, here we had e to the x. This polynomial of degree 1 is multiplied by an exponential function. So in our particular solution, we have to multiply this by e to the x. because we are looking for a function that derivative of that function and second derivative of that function combined by the function itself be equal to this. So this is our guess for the particular solution. Now we want to find these undetermined coefficients. For finding the value of a and b, we have to find y prime, take derivative of this, and y double prime, and then we have plug in those functions in here. And then by equating left side and right side coefficients, we can find a and b. So now we have to find y prime and y double prime. Y prime is derivative of this function. For finding derivative of this function, note that we have ax plus b times by e to the x. So we have to use product rule. Derivative of the bracket, derivative of ax is a, derivative of constant b is 0, so derivative of the bracket is a times by e to the x plus, write the first function which is ax plus b, multiply by derivative of e to the x, and derivative of e to the x is e to the x. So this is y prime. Now we have to take derivative of this again, y double prime. Derivative of a e to the x is a e to the x. Because a is a constant, there's no need to do any product. A is a constant, we don't have any variable. Just write a and take derivative of e to the x, which is e to the x. But for finding derivative of this part, again we have to use product. But note, add attention here, this expression is again the original function, so derivative of this is again all of this. So we take derivative of this part, which is a times by second function e to the x plus, again write the first part, multiply by derivative of second function. So this is y double prime. Now we have to plug in these functions in here. Y double prime, which is this, a e to the x plus a e to the x plus this ax plus b times e to the x minus y prime, so minus this. Don't forget to apply minus to every term here, so minus a e to the x minus ax plus b e to the x, and finally minus 2y, so minus 2 times the original function ax plus b e to the x, and all of these should be equal to this. This should be equal to 6x minus 4 e to the x. Let's simplify the left side. Note that this a e to the x and this a e to the x cancel each other, and this term also cancel each other. So we have only this a e to the x minus this minus 2 bracket ax plus b times e to the x, and this should be equal to 6x minus 4 times e to the x. If we multiply this in e to the x, we have a e to the x minus 2ax e to the x minus 2b e to the x. Note that first we multiply these two in the bracket, and then we multiply each term in the bracket by e to the x, which we get this. And this should be equal to If we multiply 6x and negative 4 by e to the x, we have equals to 6x e to the x minus 4 e to the power of x. Now, because we want to equate the coefficient of corresponding term in the left side with the coefficient of the terms in the right side, so it's better to factor the coefficients of the common terms. Note that this term has e to the x and this term has e to the x. So from these two only, not from this. We want to equate this by this term. So only from these two we factor e to the x. If we factor e to the x from these two terms, we have a minus 2 minus 2ax e to the x. This should be equal to 6x e to the x minus 4 e to the x. Now we want to equate the corresponding terms, the coefficient of corresponding terms. What is coefficient of x e to the x here? 6. What is coefficient of x e to the x in here? Negative 2a. So negative 2a must be equal to 6x e to the x. Sorry, only 6. Coefficient of x e to the x is negative 2a and coefficient of x e to the x is 6. So negative 2a must be equal to 6. And what is coefficient of e to the x here? Negative 4. What is coefficient of e to the x in the left side? A minus 2b. Now, from the first equation, a is negative 3. If we divide both sides by negative 2, a is negative 3. If we plug in this here, we have negative 3 minus 2b equals negative 4. If we move negative 3 to the other side, we have negative 1. Negative 1 divided by negative 2, b is 1/2. So this is the value of b and this is the value of a. If we plug in these values here in y, the particular solution, so the particular solution equals to negative 3x plus b 1/2 e to the x. So this is the particular solution. And this was the complementary solution. If we add them up, then we can find the general solution. So y, the general solution of this differential equation, the general solution y equals to the complementary solution, c sub 1 e to the 2x plus c sub 2 e to the negative x plus this negative 3x plus 1/2 times e to the x. This is the general solution of this differential equation. Before we do the next example, note that when we write here the particular solution, always we have to check the terms in the particular solution with the terms in the complementary solution. If, attention to this point, it's very important, and you will see this difference in the next example. We have to check every term here with every term here. When we write the particular solution, as we did here, if any terms in the particular solution be the same as any term in the complementary solution, then in the particular solution we have to multiply the particular solution by x to prevent the duplication of the terms. So we have to always check to make sure that none of the terms in the particular solution are common with the terms in the complementary solution. If any common term happens between the particular solution and the complementary solution, we have to multiply the particular solution terms by x to prevent this duplication. And we will see an example in this regard in the next example. But here, none of the terms here appeared here. Note that here we have e to the x. We don't have any e to the x here. We have e to the 2x and e to the negative x. So nothing here is duplicated here. But in the next example, we will see an example that duplication happens. And to prevent that, we have to multiply the terms here by x. Let's move to the next example. Y double prime plus y equals 2 cosine x. Note that again the general solution is the sum of complementary solution and particular solution. For finding the complementary solution, always first we have to solve the corresponding homogeneous equation. So we set right side equals 0. We set left side actually equals 0. So y double prime plus y equals 0. By solving this equation, we can find the complementary solution. And for solving the complementary solution, first we write a characteristic equation, r squared plus 1 equals 0. For solving this, again, you can use quadratic formula or simply move 1 to the other side equals negative 1, take a square root. So r equals plus minus a square root of negative 1. But we named a square root of negative 1 I, so plus minus I. But don't forget, here the real part of the solution is 0, so you can write it as 0 plus minus I. Now in this form, it's more clear that a value is 0 and b value, the coefficient of I here is 1 because we have 1 I. So b is actually 1. And if you remember, when we have complex roots like here, when we have a root in the form of a plus minus bi, if you remember, y equals to the complementary solution in general equals to e to the ax, which here a is 0, times by c1 cosine bx plus c sub 2 sine of bx. And here b is 1. So let's back to our question. So here the complementary solution for this equation is e to the 0x, but e to the 0 is 1, so it's not necessary to write it at all. So c sub 1 only, because e to the 0 is 1, 1 times anything is the same thing. So c sub 1 cosine of b is 1, so cosine x plus c sub 2 sine of x. Again, here I should mention that if you are not familiar how to find the solution of a homogeneous differential equation, watch my video related to homogeneous differential equations. This is our complementary solution. Now we want to find the particular solution, the solution that is related to the non-homogeneous part of the equation. First, we have to write the form of the particular solution. Because here we have a trig function, the only function that derivative or second derivative of that function plus that function equals cosine of x is only sine or cosine. So we guess that the particular solution, the form of the particular solution should be something like this: a cosine of x plus b sine of x, which completely makes sense the derivative of cosine or sine can make again a cosine. Note that it doesn't matter you have only sine or cosine. Whenever you have a sine or cosine, you have to put both of them here in your particular solution. Yes, it is possible that one of these coefficients be 0, but you are not sure which one is 0. So always, it doesn't matter. You have only cosine, sine, or both in the other side. You have to put both of the functions here. So even though we have only cosine here, we have to put cosine and sine, and of course with undetermined coefficients, with unknown coefficients. But note that when we look at this and we look at our complementary solution, we can see that we have common terms between this and this. Don't care to the coefficient, just focus on the terms. Here we have cosine of x, and here exactly we have cosine of x. If, for example, here we have cosine 2x, no, they are not common, but cosine of x and the same function appeared here. Also, sine of x is appeared here. So, to prevent this, when the particular solution has common term with complementary solution, to prevent this duplication, multiply the particular solution by a power of x, x to the 1, x to the 2, but the smallest power of x that prevents that duplication. Here, if we multiply this by x, then this x prevents the duplication. Now we don't have cosine of x, we have actually x cosine of x and x sine of x. Suppose that here also we had something like c sub 3 x sine of x. Then again x sine of x is duplicated here. How we can prevent that? Instead of multiplying x, multiply x2. If x2 is also appeared here, multiply x3. So you have to multiply a degree of x, always the minimum degree, but a degree of x that prevents duplication. And usually x does the job. As you can see, x times cosine of x and x times sine of x is not appears here. But if x is not enough, multiply x2, multiply x3, the minimum degree that prevents duplication. So the particular solution is in this form. And for finding the unknown coefficients, we have to find y double prime. For finding y double prime, first we have to find y prime. For finding the derivative of this function, we have to use product rule because we have x times by this bracket. Maybe you prefer to multiply x in the bracket first, then you find the derivative. Anyway, you have to use product rule. It's up to you which method you prefer. I will continue with this form. Y prime, derivative of this, equals derivative of x is 1 times by second function, a cosine of x plus b sine of x, plus write the first function, which is x, times by derivative of second function, negative a sine of x plus b cosine of x. Second derivative equals to derivative of a cosine of x is negative a sine of x plus b cosine x. Now here again we have product rule. Derivative of x is 1 times by the bracket negative a sine x plus b cosine x. Now we have to write the first function, which is x times by derivative of the bracket negative a cosine x minus b sine x. Now if we plug in y prime here and y here, we have negative a sine of x, and negative a sine of x is negative 2a sine x. b cosine x and b cosine x is 2b cosine x. And we have here, if we multiply x, negative ax cosine x minus bx sine x plus y. Y is this. So plus, let's multiply first, then write y. Ax cosine x plus bx sine x, and this should be equal to the right side of the equation, which is 2 cosine x. Now if you look at the left side of your equation, you can see that this term cancels with this and this cancels with this. So the only term that remains in the left side is this. So we have negative 2a sine x plus 2b cosine x equals 2 cosine x. Now we are ready to equate the coefficient of corresponding terms equal to each other. What is coefficient of cosine of x in the right side? 2. What is coefficient of cosine of x in the left? 2b. So 2b equals 2. What is coefficient of sine of x here? 0. We don't have any sine of x. What is coefficient of sine of x in the left side? Negative 2a. From this equation, b is 1. From the second equation, a is 0. So the particular solution equals to a is 0. 0 times cosine is 0. So only we have b sine of x. b is 1, so sine of x, and multiply by x. So x sine of x is the particular solution, which if we add this to the complementary solution, we can write our general solution. So the general solution of this differential equation, y equals to this c sub 1 cosine x plus c sub 2 sine x plus this, plus particular solution, plus x sine x. And this is the general solution of this differential equation. I hope by watching this video you have learned a bit more about solving non-homogeneous second order differential equations. In the next videos, I will show you more examples about this type of differential equations. By doing more examples, you can get more familiar with the method of undetermined coefficients. If you liked this video, please subscribe in my channel.